Everything around you, from the air you breathe to the stars above, came from nothing. We are about to trace the entire story of the cosmos, answering 30 of the most profound questions ever asked. You will discover how a single point of infinite density gave rise to every galaxy, planet, and law of physics. We will explore what sparked the Big Bang and confront the mysterious force that is now tearing the universe apart. What single cosmic mystery has always captivated your imagination? What set the cosmos into motion is the ultimate origin story. At the very beginning, our entire universe was compressed into an incomprehensible state known as a singularity. This was a point of infinite density and infinite temperature, where all the matter and energy that would ever exist was contained within a volume smaller than a single atom. The laws of physics, as we understand them, simply break down under such extreme conditions. This makes the question of what happened before the Big Bang particularly tricky. In fact, many physicists argue that the concept of a before might not even be meaningful because time itself began with that initial expansion. There was no time for anything to happen before time existed. So instead of searching for a single cosmic trigger, scientists look to the fundamental quantum realm for clues. One leading idea involves quantum fluctuations. Even in the pure nothingness of empty space, according to quantum mechanics, tiny particles of matter and antimatter spontaneously blink in and out of existence. It is possible that our entire universe is the result of one such fluctuation on a colossal scale, a random bubble of energy that inflated into everything we see. Another compelling theory suggests a cosmic bounce. Perhaps our Big Bang was not a true beginning, but rather the rebound of a previous universe that had collapsed in on itself. This cyclical model of cosmic death and rebirth offers an elegant alternative to a singular creation event. Ultimately, the initial conditions of the universe are a window into the most fundamental laws of physics, challenging us to reconcile the vast scale of general relativity with the tiny, probabilistic world of quantum mechanics. The question of what came before the Big Bang immediately confronts a profound paradox. To even speak of a before assumes that time already existed, a framework in which events could unfold. But if time itself was born in that initial fireball, then the idea of a prior moment becomes a logical impossibility. It is like asking what is north of the North Pole. The question itself might be flawed, grounded in an intuition that does not apply to the reality of cosmic origins. This forces us to reconsider the very nature of time, not as a universal constant that always was, but as a property that emerged from a more fundamental and still mysterious state. To navigate this conceptual maze, scientists have proposed some truly mind-bending ideas. One compelling theory is the cyclic model, which suggests our universe is not the first and only one. In this view, the cosmos undergoes an endless series of expansions and contractions. What we call the Big Bang was not a beginning from nothing, but a violent rebirth, a great bounce from a previous universe that had collapsed into an ultra-dense state. This elegantly removes the need for an absolute starting point, placing our existence within an infinite, timeless cycle of death and renewal. Another radical concept is eternal inflation, which paints a picture of a much larger and older multiverse. In this scenario, our entire observable universe is just one bubble in a vast, ever-expanding cosmic foam. New bubble universes are constantly budding off from this inflating background, each with its own unique laws of physics. Our Big Bang would simply mark the moment our particular bubble began to form and cool. In this multiverse, there is no single beginning, just an endless branching tree of realities. Then there is the philosophical stance that the universe simply popped into existence from nothing, a notion that seems to defy all logic. Yet, when we apply the bizarre rules of quantum mechanics, where particles spontaneously appear and vanish, the idea becomes slightly less strange. Perhaps the ultimate state of nothingness is inherently unstable, and our universe is the ultimate quantum fluctuation. Each of these theories grapples with the profound unease of a true beginning, challenging not only our scientific models but our most basic understanding of reality itself. This initial expansion was far more violent and rapid than anyone could have imagined. In the very first sliver of a second, the universe did not simply swell. It underwent a staggering growth spurt known as cosmic inflation. Think of it like this: you have a tiny speck smaller than a single proton. Then, in a time interval so brief it defies comprehension, that speck ballooned to become larger than our entire observable universe is today. This was not an expansion into empty space. Space itself was stretching, carrying the nascent energy of the cosmos with it. This incredible idea solves two of the biggest puzzles in cosmology. The first is the horizon problem. When we look at the cosmic microwave background, the ancient afterglow of the Big Bang, we see that it has the same temperature in all directions. This is deeply strange. How could regions on opposite sides of the sky, which seemingly never had time to communicate or share heat, be so perfectly uniform? The answer is inflation. Before this rapid expansion, the entire observable universe was a tiny, connected patch. It had ample time to even out its temperature. Then inflation blew that tiny, uniform patch up to a colossal size, locking in that sameness across the vast cosmos we see now. The second puzzle is the flatness problem. Measurements show the overall geometry of our universe is incredibly flat, like a perfectly stretched sheet. For it to be this flat after billions of years of evolution, its initial conditions had to be fine-tuned to an absurdly precise degree. Inflation provides an elegant solution. Just as blowing up a balloon makes its surface appear flatter and flatter, the hyper-fast stretching of space during inflation ironed out any initial curvature, leaving the universe we observe remarkably flat. But inflation did more than just solve old problems. It planted the seeds for everything to come. During this explosive period, the quantum foam of empty space was also being stretched. Microscopic quantum fluctuations were magnified to cosmic proportions, creating tiny ripples in the density of matter and energy. These ripples became the gravitational seeds around which all future structure would form. Every galaxy, every cluster of galaxies, and the vast cosmic web that connects them all grew from those tiny imperfections imprinted during inflation's first fleeting moments. The universe was no longer just a smooth, featureless soup. It had a blueprint for greatness. That rapid stretching, known as cosmic inflation, required a phenomenal engine. The leading theory proposes a strange new force, an inflationary field that permeated the newborn cosmos. Think of it like a bizarre hill. As this field rolled down its slope, it released immense energy that caused space to expand at a staggering, exponential rate. This field is often called the inflaton field, and its behavior was unlike anything in our current universe. For a fleeting moment, it dominated everything, pushing galaxies apart before they could even form. But this could not last forever. Just like a ball rolling down a hill eventually settles in a valley, the inflaton field reached the bottom of its energy landscape. When it did, it decayed. The tremendous energy locked within the field was suddenly released, flooding the universe with a hot, dense soup of fundamental particles and radiation. In that instant, the grand expansion of inflation ended, and the more familiar, gradual expansion of the Big Bang fireball began. The entire observable universe was reheated in a flash, creating the primordial plasma from which everything would later condense. The evidence for this incredible sequence of events is written across the sky. The cosmic microwave background, that ancient afterglow from the universe's infancy, is not perfectly smooth. It contains tiny, faint variations in temperature, like a subtle pattern of hot and cold spots. These imperfections are the fossilized imprint of those original quantum fluctuations, stretched to cosmic sizes during inflation. They match the predictions of inflationary theory with stunning precision. Furthermore, the overall geometry of the universe, which we observe to be remarkably flat, is a direct consequence of that rapid stretching, which ironed out any curvature like a cosmic steamroller. This is why most cosmologists see inflation not as a wild guess, but as a cornerstone of modern science. It elegantly explains the universe's large-scale structure, its uniformity, and its geometry, all in one powerful framework. It transformed a featureless singularity into a canvas subtly prepared for the creation of stars, galaxies, and ultimately us. To understand the first second, we must abandon all intuition about reality as we know it. This was a time of almost pure energy, a searing, dense fireball where the temperature was so high that the fundamental forces of nature were indistinguishable from one another. In the very first instant, during what is called the Planck epoch, all four forces, gravity, electromagnetism, and the strong and weak nuclear forces, were fused into a single, unified superforce. The cosmos was a chaotic, frothing sea where space and time themselves lost their familiar meaning. As the universe expanded and cooled at a breathtaking rate, this perfect symmetry began to shatter. First, gravity peeled away, carving out the fabric of space-time. Then, the strong nuclear force, which binds atomic nuclei together, separated from the electroweak force. For a fleeting moment, the universe was a soup of exotic particles and radiation, a state so energetic that even the most basic building blocks of matter could not hold their form. This was the era of the quark-gluon plasma. Quarks and gluons, the constituents of protons and neutrons, roamed freely, unable to bind together. It was a perfect, scalding liquid, the hottest and densest state of matter possible. As the temperature continued to plummet, a critical threshold was crossed. The universe cooled enough for the final separation, splitting the electroweak force into the electromagnetic force and the weak nuclear force. With this last great divorce, the stage was finally set. The four fundamental forces we recognize today were now distinct, each governing its own domain of reality. This cosmic cooling allowed the free-roaming quarks and gluons to finally clump together, forming the first protons and neutrons. In less than a single second, the universe transformed from a unified, featureless blaze into a structured arena with distinct rules and particles, laying the essential groundwork for every atom that would ever exist. With the fundamental forces now set in place, the universe was ready to build its first permanent structures. The chaotic quark-gluon plasma, a searing liquid of unbound particles, could not last. As the cosmos continued to expand and cool, it crossed a critical temperature threshold. Suddenly, the quarks and gluons, which had been roaming freely, found themselves trapped. The force that binds them, the strong nuclear force, became powerful enough to overcome the immense thermal energy that was keeping them apart. In a process called confinement, quarks snapped together in groups of three, forming the very first protons and neutrons. This was the moment the building blocks of atomic nuclei were forged from the primordial fire. The universe was now a scorching hot, dense soup of these new particles, constantly colliding with one another. For the first few minutes, a frantic dance of creation and destruction unfolded. Protons and neutrons slammed together, trying to form the first atomic nuclei. But it was still too hot for anything complex to survive. The intense radiation would immediately blast any newly formed nucleus apart. This delicate balance between the force of collisions and the power of destructive radiation set the stage for the next great act, Big Bang nucleosynthesis. As the temperature plummeted further, falling below 1 billion degrees, the tide finally turned. The photons of radiation lost their destructive power and stable bonds could form at last. For a brief window of about 17 minutes, the entire universe acted as a cosmic fusion reactor. A single proton, which is just a hydrogen nucleus, could capture a neutron to form deuterium, a heavy form of hydrogen. Once deuterium was stable, a cascade of reactions began. deuterium nuclei collided to form helium, specifically the helium-4 isotope with 2 protons and 2 neutrons. This process was incredibly efficient, converting nearly all the available neutrons into helium nuclei. When the universe cooled enough to stop the fusion reactions, the elemental census was set. For every 16 particles of matter, about 12 were single protons, which became the nuclei of hydrogen atoms. The other 4 were bound into helium nuclei. This left the young cosmos composed of roughly 75% hydrogen and 25% helium by mass. Only trace amounts of other light elements were forged, like deuterium, helium-3, and a tiny sprinkling of lithium. Every single bit of the hydrogen in the water you drink and most of the helium in a party balloon was created in those first few explosive minutes. This primordial recipe still defines the universe today, as over 99% of the ordinary matter you see remains hydrogen and helium, a direct echo from its fiery birth. This primordial recipe of hydrogen and helium presents a profound puzzle because, according to our best theories, it should not exist at all. The Big Bang should have created equal amounts of matter and its strange mirror image antimatter. For every proton born, an antiproton should have been created. For every electron, a positron. And when a particle meets its antimatter twin, they annihilate in a flash of pure energy. So if matter and antimatter were made in perfect balance, the entire universe should have self-destructed in a grand, final burst of light, leaving behind a cosmos filled with nothing but radiation. The simple, undeniable fact that you are here to ponder this question means something must have gone wrong, or perhaps something went wonderfully right. A tiny imbalance, a cosmic preference for matter over antimatter, allowed a small fraction of matter to survive the great annihilation. This mystery of why there is more matter than antimatter is known as the problem of baryogenesis. The Russian physicist Andrei Sakharov outlined the 3 essential conditions needed for this asymmetry to arise. First, the laws of nature must allow for processes that treat matter and antimatter differently, a phenomenon known as CP violation. Second, the universe must have been in a state of thermal disequilibrium, meaning it was not perfectly uniform and balanced. And third, interactions that change the total number of particles, called baryon number violation, must have been possible. All 3 of these conditions had to be met in the early universe to leave behind the 1/billionth surplus of matter that makes up everything we see. Scientists are now hunting for the physical processes that could have satisfied Sakharov's conditions. The most promising searches are happening deep underground in massive particle accelerators like the Large Hadron Collider. Here, physicists smash particles together at nearly the speed of light, recreating the energetic conditions of the early universe. They are meticulously studying rare particle decays, looking for any tiny deviation, any hint that nature has a subtle preference for matter over antimatter through CP violation. Every anomalous reading, every unexpected result, could be the clue that unravels this cosmic mystery and explains why a universe of something was able to emerge from a potential nothingness. The survival of that 1/billionth portion of matter set the stage for everything, but it could not have built the cosmos alone. A deeper, more profound mystery was already at work, an invisible force sculpting the universe from the shadows. This is the enigma of dark matter. We have compelling evidence that this strange substance exists, not because we can see it, but because we can see what it does. Look at a spinning galaxy. The stars on the outer edges are whirling around at tremendous speeds. According to the laws of gravity, all that visible matter, the stars and gas in the inner parts of the galaxy, should not provide enough gravitational pull to hold these fast-moving outer stars in orbit. They should be flung off into intergalactic space, yet they are not. Something with immense gravity, something we cannot see, must be holding them in place. This something is a massive, invisible halo of dark matter enveloping every galaxy. Another stunning piece of evidence comes from gravitational lensing. Einstein showed that massive objects warp the fabric of space-time, bending the path of light itself. When astronomers look at huge galaxy clusters, they often see distant galaxies behind them appearing stretched and distorted into faint arcs. The amount of bending is far too great to be caused by the cluster's visible stars and gas alone. There must be an enormous amount of unseen mass, dark matter, creating this cosmic magnifying glass. This mysterious substance does not interact with light at all, which is why it is invisible. It does not emit, absorb, or reflect any form of electromagnetic radiation. It simply does not care about light. It only interacts with the universe through gravity, and this gravitational dominance was absolutely essential for our existence. In the early universe, after the Big Bang, ordinary matter, the protons, neutrons, and electrons that make up our world, was under intense pressure from radiation. This pressure prevented matter from clumping together effectively. Dark matter, however, was immune to this radiation. Since it does not interact with light, it was free to start collapsing under its own gravity much earlier. It formed vast, invisible webs and halos, a cosmic scaffolding that stretched across the nascent cosmos. This dark matter framework provided the gravitational wells, the seeds of structure that ordinary matter could then fall into. Once the universe cooled enough for radiation's push to weaken, the hydrogen and helium gas was irresistibly drawn into these dark matter concentrations. Without this invisible skeleton to gather it, ordinary matter would have remained a diffuse, thin haze, never coalescing into the magnificent galaxies and stars we see today. Dark matter is the unseen architect of the visible universe, the silent partner whose gravitational hand guided the formation of every structure, from the smallest dwarf galaxy to the largest cosmic web. Yet this invisible cosmic architect now faces a powerful and mysterious rival. In the late 1990s, two independent teams of astronomers made a discovery so shocking it upended our entire view of the cosmos's future. They were measuring the distances to extremely far-off supernova, using them as cosmic mile markers to track how the expansion of the universe had changed over time. Everyone expected to find that the gravitational pull of all the matter in the cosmos was slowing the expansion down. Instead, they found the exact opposite. The universe's expansion is not slowing at all, it is accelerating. Galaxies are flying apart from each other at a faster and faster rate. This revelation pointed to the existence of a mysterious, repulsive force that is stretching the very fabric of space itself. Scientists call this force dark energy. The leading candidate for what dark energy could be is something known as the cosmological constant. This is an idea that Albert Einstein himself first proposed and then later famously discarded. It represents a form of energy that is an intrinsic property of empty space itself. Think of the vacuum of space not as a true nothingness, but as a seething foam of virtual particles that constantly pop in and out of existence. This quantum activity gives every tiny cubic centimeter of space a tiny, innate energy that pushes outward. On the scale of our daily lives, this effect is immeasurably small and completely unnoticeable. But across the vast, empty expanses between galaxies, the collective push of this dark energy becomes overwhelming, dominating the cosmos and driving its accelerated expansion. This discovery completely reshapes the ultimate fate of the universe. In a cosmos dominated by dark energy, the acceleration will only continue to increase. Over trillions of years, distant galaxies will be pushed away so far and so fast that their light will no longer be able to reach us. The observable universe will effectively shrink, leaving any future civilization with a sky that is utterly black and empty, isolated in a sea of darkness. All evidence of a grander cosmos will have vanished beyond an invisible horizon. The great cosmic structures that dark matter helped to build are now being steadily torn apart by the relentless push of dark energy, setting the stage for a cold, lonely, and isolated end. That invisible tug of war between dark matter and dark energy set the stage for one of the most transformative events in cosmic history. For nearly 400,000 years, the universe remained a scorching, opaque fog. It was a brilliant, blinding plasma, so hot that electrons were ripped away from atomic nuclei, creating a seething soup of charged particles. Photons of light could not travel any meaningful distance in this dense chaos. They were constantly bouncing off free electrons, scattered in every direction, trapped in a relentless pinball game. The entire cosmos was an impenetrable, glowing blaze. But the universe was still expanding, and as it expanded, it cooled. It crossed a critical temperature threshold, dropping to around 3,000 degrees Kelvin. At this moment, everything changed. The universe finally became cool enough for electrons to be captured by atomic nuclei, forming the first stable, neutral atoms. This pivotal event is called recombination. Primarily, simple hydrogen atoms formed with a single electron orbiting a single proton. Helium atoms formed as well. This sudden clearing of free electrons was like a cosmic fog lifting. With no more loose electrons to scatter them, the photons that had been trapped for millennia were suddenly set free. For the first time, light could travel across the universe in straight lines. Space became transparent. In that single, magnificent instant, the universe went from an opaque fireball to a transparent, dark expanse, illuminated only by the glow of this newly liberated light. That primordial flash, now stretched and cooled by 14 billion years of cosmic expansion, still fills the entire sky today. We detect it as a faint, uniform microwave signal, the cosmic microwave background radiation. It is the oldest light we can ever see, a baby picture of the universe capturing the moment it became recognizable, the moment the first atoms brought light to the cosmos. That ancient flash of light, set free when the first atoms formed, is still washing over us today. We know it as the cosmic microwave background, a faint whisper of radiation that fills every corner of the sky. It is the oldest light in the universe, a fossil from its infancy, and it holds secrets about everything from its birth to its ultimate fate. This cosmic echo was discovered entirely by accident. In the 1960s, two radio astronomers, Arno Penzias and Robert Wilson, were working with a giant horn antenna in New Jersey. They were plagued by a persistent, mysterious static that came from every direction, a faint hiss that would not go away no matter what they did. They even famously cleaned out a pair of nesting pigeons, thinking their droppings were the cause, but the noise remained. This annoying background hum was in fact the cooled remnant of the Big Bang's initial fireball, a discovery that would win them the Nobel Prize. This was the cosmic microwave background, the afterglow of creation itself. Since that chance discovery, scientists have launched sophisticated satellites to map this ancient light with incredible precision. Missions like COBE, WMAP, and Planck have scanned the entire sky, creating detailed baby pictures of the universe. What they found was a nearly uniform sea of microwave radiation, with a temperature of just 2.7 degrees above absolute zero. But this sea is not perfectly smooth. It is imprinted with tiny variations, minuscule hot and cold spots that differ in temperature by only about 1 part in 100,000. These tiny ripples are the most important part of the story. They are the imprint of the original quantum fluctuations from the inflationary period, stretched to cosmic proportions. They represent the seeds of all future structure. Slightly denser regions, seen as slightly warmer spots in the background, had a little extra gravitational pull. Over billions of years, that extra tug drew in more and more dark matter and gas. These tiny overdensities grew into the first stars, which gathered into galaxies, and those galaxies clustered into the vast cosmic web we see today. Every galaxy, including our own Milky Way, originated from one of these faint imperfections. By studying the precise patterns of these temperature variations, cosmologists can read the universe's vital signs like a cosmic doctor. The characteristics of these ripples tell us the universe is 13.8 billion years old. They confirm that its geometry is flat, just as inflation predicted. And they provide the most accurate census of its composition, revealing that ordinary matter, the stuff of stars and planets, makes up less than 5% of the cosmos. The rest is the mysterious dark matter and dark energy that govern its evolution. The cosmic microwave background is our most direct link to the universe's fiery beginning, a time capsule that continues to reveal the deepest truths of our cosmic home. After that primordial glow faded, the universe plunged into an abyss of silence. For millions of years, a profound darkness reigned during what we call the cosmic dark ages. There were no stars, no galaxies, no sources of light at all. The cosmos was just a vast, expanding sea of neutral hydrogen and helium gas, still and dark. But beneath this apparent calm, an invisible architecture was at work. The subtle ripples imprinted in the cosmic microwave background were more than just temperature variations. They were regions of slightly higher density. These pockets of extra mass, dominated by dark matter, exerted a stronger gravitational pull. Over eons, these dark matter halos began to steadily draw in the surrounding clouds of primordial gas. This was a slow, relentless process, a gravitational gathering that would eventually break the long cosmic night. The gas, composed almost entirely of hydrogen and helium, began to swirl and compress within these growing dark matter wells. As the gas clouds collapsed, they fragmented into smaller, denser clumps. At the heart of these clumps, the pressure and temperature began to skyrocket. When the core of a gas clump reached a staggering 10 million degrees, a monumental threshold was crossed. The immense heat and pressure forced hydrogen nuclei to overcome their natural repulsion and fuse together, creating helium and releasing a tremendous burst of energy in the process. Nuclear fusion had begun. The first stars were born. These pioneering suns, known as Population 3 stars, were nothing like the stars we see today. They were behemoths, likely hundreds of times more massive than our own sun. Pure and simple, forged only from the pristine hydrogen and helium of the Big Bang, they burned at ferocious temperatures, shining with a brilliant bluish-white light that was intensely rich in ultraviolet radiation. Their immense size, however, came at a cost. They lived fast and died young, consuming their nuclear fuel in just a few million years before exploding in cataclysmic supernova. These first stellar deaths were not an end, but a vital new beginning. Within their searing cores, these giant stars forged the first heavier elements, atoms like carbon, oxygen, and iron. As they exploded, they scattered these newly minted elements far and wide, polluting the pristine cosmic gas with the raw materials for rocky planets, water, and even life itself. The death of the first stars seeded the cosmos with the chemical diversity needed for everything that was to come, from the planets that would orbit future stars to the very molecules that make up our bodies. These first stellar explosions did more than just seed the cosmos with new elements. They also left behind incredibly dense gravitational traps. The most massive of those early stars collapsed not just into supernova, but directly into black holes, the universe's first anchors of gravity. These primordial black holes were likely the seeds for something far grander, the supermassive black holes that now lurk at the heart of nearly every galaxy, including our own Milky Way. How these cosmic monsters grew so large so quickly remains an active mystery. One theory suggests they formed from the direct collapse of enormous clouds of primordial gas, so massive and dense that they bypassed star formation entirely and collapsed straight into a black hole. Another possibility is that they grew from those first stellar mass black holes, which then gorged themselves on the surrounding gas and merged with one another in a frantic feeding frenzy during the crowded early universe. Regardless of their origin, once established, these supermassive black holes became far more than just passive vacuum cleaners. They evolved into powerful regulators, their activity dictating the very fate of the galaxies they inhabited. When a black hole is actively feeding, the infalling matter doesn't just vanish. It forms a superheated, spinning disk of material called an accretion disk, which glows with the intensity of billions of stars. This creates a quasar, one of the most luminous objects in the universe. Along the black hole's poles, intense magnetic fields can funnel some of the inflowing matter into powerful, focused jets that blast out across space for thousands of light years. These jets pump colossal amounts of energy back into the surrounding galaxy. This process, known as feedback, is a cosmic balancing act. In a galaxy's youth, this energy can compress gas clouds, actually triggering waves of new star formation. But if the black hole becomes too active, its quasar winds and jets can have the opposite effect. They can violently heat and blow away the galaxy's vast reservoirs of cold gas, the very fuel needed to make new stars. This shuts down star formation, effectively putting the galaxy into retirement. A supermassive black hole acts like a cosmic thermostat, preventing its host galaxy from growing too large too fast. Without this regulation, galaxies might have burned through their fuel in a brief, brilliant flash, leaving no time for stable solar systems or planets like our own to slowly form and evolve. The silent, dark heart of a galaxy is not a destroyer but a sculptor whose violent appetite helps write the story of cosmic structure. That universal expansion rate provides our first major clue to the cosmos's age. The discovery that galaxies are all rushing away from us, with more distant ones moving faster, gives us a powerful tool. We call this relationship the Hubble constant, a number that tells us how fast the universe is expanding today. Think of it like rewinding a cosmic film. If you know how fast the galaxies are moving apart now, you can calculate backwards to the moment when they were all crushed together. This reverse calculation points directly to a beginning roughly 13.8 billion years ago. But this method relies on precise measurements of both the distances to faraway galaxies and their velocities, a challenging task that has seen refinements for nearly a century. A second, completely independent line of evidence comes from the oldest light we can see. The cosmic microwave background is a time capsule from when the universe was only 380,000 years old. By mapping the subtle temperature ripples in this afterglow with satellites like Planck, cosmologists can determine the universe's ingredients and geometry with incredible precision. They can essentially take this baby picture and run the clock forward using our well-tested laws of physics. The way those tiny fluctuations grow into the cosmic web of galaxies we see today is exquisitely sensitive to the universe's age. This detailed modeling of the cosmic microwave background also points to an age of 13.8 billion years. Finally, we can look at the oldest objects within the universe itself to set a firm lower limit. In our own Milky Way galaxy, we find ancient globular clusters, dense swarms of stars that formed long before our sun was even a glimmer. By studying the light from these stars, astronomers can determine their composition and, using stellar evolution models, calculate their ages. The very oldest of these stars are consistently dated to be over 13 billion years old. The universe simply has to be older than the stars it contains. The stunning convergence of these three separate methods is what gives scientists such profound confidence. The expansion rate of the present, the fossilized light from the past, and the ancient stellar chronometers all tell the same story, independently confirming that we live in a cosmos 13.8 billion years old. This question of the universe's scale is perhaps the most dizzying of all. To grasp it, we must think about its shape, its geometry on the grandest scale. Scientists describe three possible fates for cosmic geometry, each tied to the amount of matter and energy the universe contains. The first is a closed universe which curves back on itself like the surface of a sphere. In this model, if you could travel in a perfectly straight line for long enough, you would eventually return to your starting point, just as a ship sailing across the ocean can circumnavigate the Earth. The second is an open universe which curves outward like a saddle, extending forever without end. And the third is a flat universe which follows the rules of classic Euclidean geometry we learned in school, where parallel lines never meet and the angles of a triangle always add up to 180 degrees. So which one is it? The evidence, primarily from the detailed maps of the cosmic microwave background, points overwhelmingly to a flat geometry. The patterns of the ancient temperature ripples are exactly what we would expect if the universe has no overall curvature. A flat geometry, in the context of Einstein's theory of general relativity, most likely implies an infinite universe. It means that space just keeps going forever without any edge or boundary. There is no center and there is no end. The sheer volume of space and the number of galaxies within it would be literally without limit. But here is the crucial caveat that keeps this concept from being entirely abstract. While the universe may be infinite, what we can ever see is not. We live within our observable universe, a finite bubble centered on us. Its edge is not a physical wall, but a horizon in time. It is the farthest distance from which light has had time to reach us since the Big Bang, a journey of 13.8 billion years. Everything beyond that cosmic horizon is forever hidden from our view, as the light from those distant regions has not had enough time to get here yet. And because dark energy is accelerating the expansion, more and more galaxies are being pushed beyond this horizon every day, vanishing from our future view. So we find ourselves in a profound situation, living in a likely infinite cosmos, yet forever trapped within a finite and slowly shrinking island of the observable. That silent, accelerating expansion driven by dark energy points toward a profoundly cold and lonely finale. The most widely accepted forecast based on our current measurements is known as the heat death or the Big Freeze. In this scenario, the universe continues to expand and accelerate forever. Galaxies will be pushed so far apart that the night sky for any surviving civilization will become utterly black. One by one, stars will exhaust their nuclear fuel and cease to shine. Even the longest-lived red dwarf stars will eventually flicker out after trillions of years. With no new stars forming, the universe will steadily grow darker and colder. Then the final decay begins. Over unimaginable timescales, even the building blocks of matter itself may not be stable. Protons, which we consider fundamental and eternal, could potentially decay, though this has never been observed. If they do, all remaining atomic matter, from dead stars to wandering planets, will gradually dissolve into a thin, uniform haze of subatomic particles and radiation. The temperature of the entire cosmos will approach absolute zero, the point where all motion stops. The universe will reach a state of maximum entropy, a final, eternal equilibrium where no energy can be extracted to do any work, and no meaningful change can ever occur again. It is the ultimate silence, but the heat death is not the only possibility on the theoretical table. Another, more violent end is the Big Rip. This depends on the exact nature of dark energy. If its repulsive force grows stronger over time, it could eventually overcome every force that holds things together. First, galaxy clusters would be torn apart. Then, individual galaxies. As the acceleration intensifies, stars would be ripped from their galaxies. In the final moments, planets would be shredded from their solar systems. Ultimately, the violent expansion would tear apart atoms, nuclei, and even the very fabric of spacetime itself. The universe would end not with a whimper, but with a catastrophic rupture of everything. There is also a more cyclical, almost poetic alternative. What if the expansion doesn't continue forever? What if the density of matter and energy is high enough for gravity to finally win? This would lead to a big crunch, a dramatic reversal of the Big Bang. The universe would stop expanding and begin collapsing back in on itself. Galaxies would rush together, the temperature would soar, and the cosmic microwave background would heat up from its faint whisper to a blazing glare. Everything would converge back toward an ultra-hot, ultra-dense state, perhaps another singularity. Some theories even suggest this singularity could then rebound, triggering a new Big Bang and birthing a fresh universe in an endless cycle of cosmic death and rebirth. For now, our best data strongly favors the cold, lonely expanse of the heat death. Yet these other possibilities remind us that the fate of the cosmos hinges on the precise and still mysterious properties of dark energy, leaving the final chapter of our universal story still waiting to be written. This single universe we have been exploring might not be alone. The concept of a multiverse suggests our cosmos is just one bubble in a vast, frothing cosmic sea, an endless collection of parallel universes. This is not mere science fiction, but a serious, albeit speculative, consequence of our leading theories of cosmic origins. The mechanism most often invoked is a refinement of cosmic inflation known as eternal inflation. Picture that initial inflationary field, the energy that drove the universe's explosive birth. According to this idea, this inflation does not stop everywhere at once. Most of this inflating space continues to stretch exponentially forever, creating an ever-expanding background. But within this rapidly swelling expanse, random quantum fluctuations can cause small pockets or bubbles to stop inflating. In each of these bubbles, the inflationary energy decays, releasing its pent-up force to create a hot Big Bang and a new universe. Our entire observable cosmos is just one such bubble within an incomprehensibly vast, eternally inflating meta-universe. Each of these bubble universes could be wildly different from our own. When a bubble forms, the way its inflationary field settles down could randomly determine the fundamental constants of nature within it. In one bubble, the strength of gravity might be 10 times stronger. In another, electromagnetism might be too weak to form atoms. We happen to live in a bubble where the constants are just right for atoms, stars, planets, and life to form, a concept that feels eerily like a cosmic version of natural selection. This offers a potential, if controversial, solution to the puzzle of fine-tuning. Why are our physical laws so perfectly calibrated for complexity? If there are an infinite number of universes with different rules, then it is no surprise we find ourselves in one of the rare, hospitable ones. The philosophical implications are staggering. It suggests that every possible reality might actually exist somewhere. A universe made entirely of crystal, another where time runs backward, or one identical to ours except you made a different choice this morning. Yet the scientific hurdle is immense. By definition, these other universes are beyond our cosmic horizon, separated from us by regions of space that are still inflating faster than light can cross. How could we ever test such a thing? Some theorists look for subtle imprints on our cosmic microwave background, a bruise left if our bubble universe ever collided with another in the distant past. Others seek mathematical consistency, arguing that if the theory that predicts the multiverse is the simplest explanation for everything we do see, then we should take seriously what it also predicts about what we cannot see. The multiverse remains a frontier of thought, a dazzling possibility that challenges not only what we know about the cosmos, but what it is even possible to know. Even the universe's baby picture holds a few unsettling secrets. Among the near-perfect uniformity of the cosmic microwave background, astronomers have stumbled upon a strange, large-scale pattern that seems to defy one of cosmology's most sacred rules. They have nicknamed this anomaly the axis of evil. The problem begins with the cosmological principle, the foundational idea that the universe is broadly the same in every direction. It has no center, no edge, and no preferred orientation. The cosmos should look statistically identical no matter where you are. Yet, when scientists study the subtle temperature fluctuations in the microwave background, they find certain patterns that are not randomly distributed. Some of the largest warm and cool spots appear to be mysteriously aligned, and their orientation seems to correlate with the plane of our own solar system. This is deeply troubling. Why would the grandest features of the entire observable universe, a fossil from long before our solar system even existed, somehow know about the flat disk of planets orbiting our sun? The chance of such an alignment happening at random is incredibly small, which suggests three possibilities, each more radical than the last. The first and most conservative explanation is that it is simply a statistical fluke. With the vast amount of data we have, sometimes strange correlations pop up purely by accident. The second possibility is that it is a systematic error, an unknown contamination in our measurements. Perhaps the data is being subtly skewed by the glow of our own galaxy, or by the way our spacecraft observes the sky. But after years of scrutiny and analysis from multiple satellites, the anomaly stubbornly persists. This leads to the third and most thrilling possibility. The axis of evil could be a genuine crack in the cosmological principle, a hint that the universe is not perfectly uniform after all. It might suggest that space itself has a preferred direction on the largest scales, a cosmic grain that we are only just beginning to detect. If true, this would force a fundamental rewrite of modern cosmology, challenging our most basic assumptions about the nature of reality. Is the universe trying to tell us it is not what we thought, or are we simply misreading its oldest message? These finely tuned constants are not just numbers in a textbook, they are the precise settings on the cosmic control panel. The strength of gravity, the mass of an electron, the force that binds atomic nuclei, if any of these values were altered by even a tiny fraction, the universe as we know it would cease to exist. Make gravity slightly stronger and stars would burn through their fuel in a flash, leaving no time for planets to form. Make the nuclear force a bit weaker and hydrogen would never fuse into helium, so no stars would shine at all. This remarkable precision is what we call the fine-tuning problem. It feels as though the cosmos was designed with life in mind, but is that truly the case, or is there another explanation? One compelling answer is known as the anthropic principle. In its simplest form, it states that we can only observe a universe that is capable of supporting our existence. We are here to ponder these constants precisely because they are set to the right values for us to be here. It is a self-selecting observation. If the laws were different, we would not exist to notice. This idea gains profound weight when paired with the concept of a multiverse. If an infinite number of universes exist, each with its own random set of physical laws, then it is no longer surprising that we find ourselves in one of the rare, hospitable ones. In most universes, the constants would be wrong, leading to a sterile, empty cosmos. We simply won the cosmic lottery, yet for many scientists, this is an unsatisfying stopping point. They seek a deeper reason, a fundamental theory that can explain why the constants have the values they do, rather than just accepting them as lucky accidents. This quest drives the search for a theory of everything, a single framework that unites all forces and particles. The leading candidate for decades has been string theory. It proposes that at the tiniest scales, the fundamental building blocks of the universe are not point-like particles, but unimaginably small, vibrating strings. The different ways these strings vibrate would give rise to all the different particles and forces we observe, much like different vibrations of a violin string create different musical notes. In this elegant picture, the laws of physics and the values of the constants would not be arbitrary. They would be the inevitable outcome of how these strings vibrate within the geometry of extra, hidden dimensions of space. String theory suggests there could be a vast landscape of possible stable configurations, each corresponding to a different universe with different laws. Our universe is just one point in this landscape. The challenge is immense as these strings are thought to be so small that devising an experiment to detect them is currently beyond our reach. The journey to understand why the laws are what they are pushes at the very frontier of human knowledge, asking whether the universe is ultimately built on a foundation of mathematical necessity, or if we are indeed living in a fortunate cosmic oasis. The quantum realm holds the secret blueprint for our entire cosmic architecture. At its heart lies a bizarre but fundamental truth that empty space is not empty at all. The vacuum of space is a seething, bubbling sea of energy. According to quantum mechanics, pairs of virtual particles and their antimatter twins spontaneously blink into existence, borrowing energy from the vacuum for an impossibly brief moment before annihilating each other and vanishing. This constant, frantic activity is known as quantum fluctuation. On the human scale, this effect is completely undetectable, but in the first fleeting instance of the universe, it was absolutely everything. During the period of cosmic inflation, when the universe expanded faster than the speed of light, something miraculous happened to these tiny quantum ripples. The violent stretching of space itself grabbed hold of these microscopic fluctuations and magnified them to an astronomical scale. A region that was momentarily slightly denser due to a random particle pair appearing was stretched into a vast, continent-sized overdensity. A region that was momentarily slightly emptier became a colossal cosmic valley. In an instant, the perfectly smooth primordial soup was imprinted with a subtle pattern of denser and less dense regions. These minute variations in density, born from the quantum foam, became the gravitational seeds for all future structure. After inflation ended and the universe cooled, gravity began its slow, patient work. The regions with a tiny bit more mass had a slightly stronger gravitational pull. Over millions of years, they began to draw in more and more of the invisible dark matter and the primordial hydrogen and helium gas. What began as a quantum whisper became a gravitational shout. These seeds grew into the first clumps of dark matter, the scaffolding upon which galaxies would be built. The gas fell into these gravitational wells, condensing and collapsing to form the very first stars and star clusters. These then gathered into proto-galaxies, which merged and evolved into the magnificent spirals and ellipticals we see today. Every galaxy, every cluster, and the vast cosmic web connecting them all can trace its origin back to those random, ghostly flickers in the first moment of time. The largest structures in the universe were ultimately sculpted by the smallest. This remarkable uniformity across the cosmos presents one of its most enduring puzzles. When we look at the cosmic microwave background, the ancient light from opposite ends of the sky, we see it has almost exactly the same temperature everywhere. This seems logical until you consider the speed limit of the universe, the speed of light. In the standard Big Bang model, there simply hasn't been enough time since the beginning for light or heat to have traveled from one of these distant regions to the other. They are like two people standing in separate, soundproof rooms, yet both decide to hum the same note at the same precise pitch without ever having spoken. How could they have coordinated this? These regions were never in causal contact, meaning information could not have passed between them to even out their temperature. This is the essence of the horizon problem, a fundamental flaw in the classical Big Bang picture. The solution requires a radical rewrite of the universe's earliest moments. Cosmic inflation provides the answer. Before the period of hyper-fast expansion, the entire observable universe was crammed into a tiny, subatomic volume. This minuscule patch was so small that every part of it was in direct contact with every other part. It had ample time to exchange energy and settle into a perfectly uniform temperature, like a single, well-stirred cup of coffee. Then inflation struck. Space itself expanded faster than the speed of light, violently stretching this tiny, uniform patch into the vast cosmos we see today. The regions that are now on opposite sides of the sky were once cozy neighbors, explaining why they share the same temperature today. Inflation did not create the uniformity. It simply took a small, balanced region and blew it up to a colossal scale, preserving that sameness across billions of light years. This elegant mechanism turns a profound mystery into a natural consequence of the universe's explosive birth. revealing how a brief moment of unimaginable stretching left its mark on the entire visible cosmos. Buried within the cosmic web of galaxies is a ghostly echo from the universe's fiery youth. This phenomenon, known as baryon acoustic oscillation, acts as a cosmic measuring tape that astronomers use to map the expansion history of the cosmos with incredible precision. To understand it, we must travel back to the universe's first few 100,000 years, when it was still a dense, hot plasma. In this searing soup, ordinary matter, which scientists call baryons, was tightly coupled with light. Gravity would try to pull the baryons inward, clumping them together, but the intense pressure from the radiation of light would push them back outward, creating a powerful spherical pressure wave that rippled through the plasma. This was, in essence, a sound wave traveling through the early universe. This back-and-forth battle between gravity's pull and radiation's push created a series of oscillations like the ringing of a cosmic bell. Then recombination happened. When the universe cooled enough to form neutral atoms, the fog cleared, and the light was set free to become the cosmic microwave background. At that very moment, the pressure waves froze in place. The baryons that were at the leading edge of these spherical sound waves were suddenly locked into a shell, creating a subtle, fossilized pattern where galaxies were slightly more likely to form. The key is the size of that shell. The waves could only travel a fixed distance before the universe became transparent, a distance dictated by the speed of sound in that primordial plasma. This distance became a standard ruler etched into the fabric of the cosmos, measuring about 500 million light-years across. This means that if you were to look at the distribution of millions of galaxies today, you would find a subtle statistical preference for pairs of galaxies to be separated by this specific, vast distance. It is the fossilized imprint of that ancient sound wave, stretched by cosmic expansion but still recognizable. By observing this standard ruler at different distances, and therefore at different eras in cosmic history, astronomers can perform a powerful test. They can measure how much the universe has stretched this ruler over billions of years. This allows them to trace the expansion rate of the universe through time, watching for the subtle shifts that reveal the influence of dark energy. It is a direct measurement of how the cosmos has grown, providing independent and robust confirmation of the accelerating expansion and helping us to further unravel the mysterious nature of the force that shapes our ultimate fate. The death of a star is one of the universe's most creative acts. Those first giant stars born from pristine hydrogen and helium were the original cosmic alchemists. Deep within their cores, under unimaginable pressure and heat, they performed a miracle, fusing the simplest elements into something new. They smashed hydrogen atoms together to make helium, and then, as their cores grew hotter, they began fusing helium itself. This process created carbon, the fundamental backbone of life. Further fusion produced oxygen, the element we breathe, and neon, which lights up our city signs. Step by step, the star built a layered onion-like structure, with heavier elements like silicon and magnesium forming in concentric shells around a core that was rapidly running out of fuel. But this stellar factory had a strict limit. The process of fusion can only create elements as heavy as iron. Forging iron actually consumes energy instead of releasing it. So when a massive star finally built an iron core, its energy production slammed to a halt. Without the outward push from fusion to counteract the immense pull of gravity, the star's core collapsed catastrophically in less than a second. The outer layers of the star, no longer supported, came crashing down at a quarter the speed of light, only to rebound off the ultra-dense core in a titanic shockwave. This is a core collapse supernova, an explosion so brilliant it can outshine an entire galaxy. In that fleeting, infernal maelstrom, the real magic happened. The flood of neutrons in the collapsing core enabled a rapid capture process, building elements heavier than iron atom by atom. This is where the gold in your jewelry was forged. This is where the uranium that powers nuclear reactors was created. The silver in a photographic film, the iodine in your thyroid, the zinc that supports your immune system, all of them were born in the heart of a dying star. The supernova then blasted these newly minted elements across light years of space, seeding the surrounding cosmic clouds with this rich chemical diversity. When our own solar system coalesced from the gas and dust of such an enriched cloud, it carried with it the legacy of countless stellar explosions. Every atom of oxygen in the air, every piece of calcium in your bones, and every trace of iron in your blood was once forged in the heart of a long-dead star. We are literally made of stardust, the recycled remnants of ancient suns that lived and died to give us a universe rich enough for planets, oceans, and life itself. That stardust from the first stellar explosions settled into a new cosmic era, one that would fundamentally reshape the universe once more. After the long silence of the Dark Ages, the cosmos was about to be flooded with a new kind of light. This pivotal chapter is known as the epoch of reionization. For hundreds of millions of years, the universe had been filled with neutral hydrogen gas, atoms that had cooled and settled after the cosmic microwave background was released. This gas was transparent to visible light, but it acted as a thick fog to the higher energy ultraviolet radiation. Then the first stars and galaxies ignited. These pioneers were not like our gentle sun. They were colossal, ferociously hot, and blazed with intense ultraviolet light. When these powerful UV photons streamed out into space, they slammed into the neutral hydrogen atoms that filled the cosmos. Each collision was so energetic that it ripped the electron right off its proton, a process we call ionization. It was as if a cosmic ultraviolet sunrise was slowly burning away a global fog. The first stars did not act alone. The earliest quasars, those brilliant beacons powered by supermassive black holes, also joined the fray. Their incredible luminosity produced even more intense radiation, helping to blast away the neutral hydrogen and create vast, growing bubbles of transparent, ionized plasma. Over hundreds of millions of years, these bubbles expanded and merged until the entire universe was once again transparent to ultraviolet light, a state it has maintained ever since. So how can we possibly observe this ancient transition? Astronomers use a clever cosmic trick, employing the most distant quasars as backlights. When we point our telescopes at a quasar from this early era, its light has traveled for billions of years to reach us. Along its journey, it passed through the clouds of neutral hydrogen that existed before reionization was complete. That hydrogen left a distinct fingerprint on the quasar's light, absorbing specific wavelengths and creating a thicket of dark absorption lines known as the Lyman alpha forest. By studying the pattern of these lines in quasars at different distances, and therefore from different times, scientists can see the fog gradually clear. Quasars from the heart of the reionization epoch show almost complete absorption, their light nearly eaten by the hydrogen fog. Those from just after the epoch show a much clearer path. This delicate forensic work on ancient light allows us to pinpoint when this great cosmic transformation occurred, revealing how the first luminous objects fundamentally altered the fabric of the universe and lit the way for everything that followed. Our own cosmic story might not be the first edition. The idea of a cyclic universe, one that dies and is reborn in an endless series, offers a breathtaking alternative to a single beginning. One of the most compelling versions of this idea comes from the Nobel laureate Roger Penrose with his theory of conformal cyclic cosmology. In this radical model, the universe does not have a true beginning or end. Instead, it consists of a series of vast epochs which Penrose calls eons. Each eon starts with its own Big Bang and expands for trillions upon trillions of years into an unimaginably vast, cold, and empty future. In this distant era, all matter has eventually decayed, black holes have evaporated, and only massless particles like photons remain, wandering through an ever-expanding void. At this point, according to Penrose's mathematics, the universe becomes so vast and empty that it loses all sense of scale. A single photon sees the entire infinite cosmos as a single point. In this strange, smooth state, the end of one eon becomes geometrically identical to the beginning of another Big Bang. The distant future of one universe seamlessly becomes the hot, dense singularity of the next in an endless cycle of renewal. But is there any evidence for such a poetic idea? Penrose believes he has found it, etched into the oldest light we can see. He and his collaborators argue that the cosmic microwave background should contain imprints from the previous eon. Specifically, they search for concentric circles of slightly warmer temperature within the CMB's map. These circles, they propose, are the ghostly echoes of immensely powerful gravitational waves, generated when supermassive black holes from the previous universe collided and merged. These ripples would have carried across the boundary between eons, leaving faint circular signatures in our own universe's baby picture. The scientific community remains deeply divided on this claim. Many astronomers argue that the patterns Penrose identifies could be statistical flukes, random noise in the exquisite data from the Planck satellite. The search for these concentric rings continues, a high-stakes detective story sifting through the fossilized light of creation. If Penrose is correct, our universe is not a one-off event but a single chapter in an infinite, timeless book, where every ending is simply a new beginning in disguise. This profound silence from the cosmos presents a puzzle that has troubled scientists for generations. We call it the Fermi paradox, named for the physicist Enrico Fermi, who, during a casual conversation in the 1950s, famously asked, "Where is everybody?" His point was simple and powerful. The universe is unimaginably vast and ancient, with billions of planets that could potentially support life. Given so much time and space, it seems statistically inevitable that other intelligent civilizations would have arisen. Some of them should have become interstellar, colonizing entire galaxies over millions of years. Their presence, whether through radio signals, probes, or massive engineering projects, should be obvious. And yet, when we listen, we hear nothing but a great, unnerving silence. This contradiction between the high probability of alien life and the total lack of evidence for it lies at the heart of one of science's greatest mysteries. One of the most unsettling explanations is the Great Filter hypothesis. This idea suggests that there is at least one enormous, perhaps insurmountable, barrier that prevents life from progressing to the stage of interstellar civilization. This filter could lie in our past. Maybe the origin of life itself from non-living chemistry is an astronomically rare fluke. Or perhaps the leap from simple single-celled organisms to complex multicellular life is the true bottleneck. If this is the case, then we on Earth are the incredible exception, the lone spark of consciousness in a sterile cosmos. The more terrifying possibility is that the Great Filter lies in our future. There could be some inevitable catastrophe that awaits all technologically advanced species. This could be self-destruction through nuclear war or climate change, a lethal pandemic, or perhaps the emergence of a runaway artificial intelligence that eliminates its creators. In this scenario, the silence is ominous, a graveyard quiet indicating that no civilization survives its own technological adolescence. Other solutions to the paradox are less bleak but equally mind-bending. Perhaps intelligent life is common, but it evolves in ways so alien that communication is impossible. Their thoughts, their technology, their very perception of reality might be so different from our own that we simply do not recognize their signals or their artifacts. They could be among us or all around us, and we would be like ants at the foot of a skyscraper, completely unaware of the civilization building above our heads. Another possibility is that space is simply too big. The distances between stars are so immense that even a civilization with advanced technology might find interstellar travel impractical or economically pointless. They could be out there, quietly tending to their own celestial gardens, with no desire or need to broadcast their existence across the void. or they might be observing us with a policy of non-interference, a cosmic prime directive, choosing to let our young civilization develop on its own without interference. The Great Silence forces us to confront our own significance or our insignificance in the grand scheme of things. Are we a precious miracle, or are we simply the first to arrive at the party, waiting in a quiet and empty universe for guests who may never come? That profound silence from the cosmos is not the only message carried on the fabric of space itself. A new sense is opening for astronomy, allowing us to feel the universe's deepest tremors. We have begun to detect gravitational waves, the ripples in spacetime predicted by Einstein over a century ago. These waves are created by the most violent events in the cosmos, like the final, spiraling dance of two black holes before they collide. As these massive objects orbit each other, they churn the very fabric of reality, sending out waves that travel at the speed of light, stretching and squeezing everything in their path by an almost infinitesimal amount. Detecting these waves requires some of the most precise instruments ever built, like the LIGO and Virgo observatories. They use powerful lasers to measure the distance between mirrors placed several kilometers apart. When a gravitational wave passes through the Earth, it minutely changes that distance by less than the width of a single proton. The fact that we can measure such a tiny distortion is one of the greatest experimental achievements in human history. But the mergers we have detected so far are just the tip of the iceberg. The real prize for cosmologists is something far more subtle and ancient, a faint hum that would be the oldest sound in the universe. This is the primordial gravitational wave background. Theorists believe it was generated in the first instance after the Big Bang, during the incredibly violent period of cosmic inflation. As space expanded faster than light, the fierce quantum turmoil of that era should have sent powerful ripples cascading through the very structure of spacetime itself. Unlike the cosmic microwave background, which is a snapshot of the universe at 380,000 years old, this gravitational wave background would come from a time far earlier, a mere fraction of a second after everything began. It would be a direct messenger from the epoch of inflation, carrying untouched information about the energy scales and physics that shaped our entire cosmos. Finding this signal is the next great frontier. It would not only confirm our theories of inflation, but could also reveal the nature of the mysterious inflated field that drove it. Current detectors are not yet sensitive enough to pick up this faint, universe-wide hum, but ambitious new projects are being planned. Space-based observatories, like the proposed LISA mission, would use lasers between satellites millions of kilometers apart to listen for these low-frequency ripples. By tuning into this primordial vibration, we could finally hear the echo of creation itself, a whisper from the very moment the universe was born. A quiet disagreement over a single number is shaking the very foundations of cosmology. This is the Hubble tension, a stubborn and growing crisis centered on one question: just how fast is the universe expanding right now? The Hubble constant should be a fixed value, a universal speed limit for cosmic expansion. Yet when scientists measure it using two different, highly trusted methods, they get two different answers. It is like using two different, perfectly calibrated rulers to measure the same table and getting two different lengths. The first method looks at the early universe using the detailed map of the cosmic microwave background from the Planck satellite. By studying the subtle patterns in this ancient light, cosmologists can run the cosmic film forward, calculating what the expansion rate must be today. This method gives us one very precise number. The second method looks at the modern universe using cosmic mile markers like Cepheid variable stars and distant supernova. These objects have known intrinsic brightness, so by measuring how dim they appear from Earth, astronomers can calculate their distance and thus measure the expansion rate directly. This method gives us another very precise number. The problem is these two numbers do not agree. They are off by just enough to be deeply troubling. the late universe appears to be expanding faster than the early universe's fossilized light says it should be. This is not a small experimental error, it is a glaring discrepancy that has survived over a decade of repeated, refined measurements. If our measurements are correct, then our model of the universe must be wrong or incomplete. This tension points toward the possibility of new physics, something missing from our standard cosmological recipe. Perhaps dark energy is not a constant force but is evolving, growing stronger over time. Maybe there is a new, unknown type of neutrino or other exotic particle that was influential in the early cosmos. Or perhaps dark matter has properties we have not yet accounted for. The Hubble tension is a cosmic alarm bell telling us that our understanding of the universe, for all its successes, still holds profound and exciting secrets. This cosmic detective story is about to receive its most powerful tool yet. The James Webb Space Telescope is not merely a new telescope, it is a time machine. Its primary mission is to gaze back into the deepest depths of the past, to capture the faint, stretched light from the very first stars and galaxies that ever formed. It achieves this with a colossal gold-coated mirror and a suite of instruments exquisitely sensitive to infrared light. Why is this infrared vision so crucial? Because as the universe expands, light from the most distant objects is stretched on its long journey to us. This cosmic stretching shifts the light from its original visible wavelength into the infrared part of the spectrum. For the earliest galaxies, this light is so stretched that it is completely invisible to telescopes like Hubble. Webb is specifically designed to see this ancient, redshifted glow, pulling back the curtain on the cosmic dark ages and witnessing the universe's first dawn. One of its most ambitious goals is to directly image the infant galaxies from the epoch of reionization, to see how they lit up the cosmic fog and transformed the universe from opaque to transparent. But Webb's revolutionary power extends far beyond our cosmic origins. It is also an unparalleled exoplanet explorer. When a distant planet passes in front of its host star, a tiny fraction of the star's light filters through the planet's atmosphere. Webb can dissect this faint whisper of light, splitting it into a spectrum. By reading this spectrum, scientists can identify the chemical fingerprints of molecules like water vapor, methane, and carbon dioxide in the atmospheres of worlds hundreds of light years away. For the first time, we are not just detecting these distant planets, we are beginning to study their weather, their climate, and their potential habitability. We are searching for biosignatures, atmospheric imbalances that could be a telltale sign of life. Every observation from this incredible observatory has the potential to answer the profound questions we have explored, from the formation of the first starlight to the chemical enrichment of the cosmos, and perhaps even to the ultimate question of whether we are alone in the universe. Our journey through cosmic history brings us face to face with the grandest puzzles still unsolved. We have charted the universe from its first spark to its vast present, yet the deepest foundations of reality remain shrouded in mystery. The true nature of dark matter and dark energy stands as perhaps the greatest enigma. We know dark matter's gravity sculpts galaxies, and dark energy drives the cosmos apart, but we have no idea what they actually are. These two invisible components make up 95% of the universe, meaning everything we see and know is just a 5% fragment floating in a sea of the unknown. Then there is the baffling mystery of the initial singularity. Our physics simply breaks down at the moment of the Big Bang. We cannot describe a state of infinite density, a point where time and space as we know them began. What, if anything, came before? Was it a true beginning or merely a transition from a previous cosmic phase? The problem of matter's survival is equally profound. Why does anything exist at all? The Big Bang should have created equal parts matter and antimatter, leading to total annihilation. Yet here we are. A tiny, 1 in a billion asymmetry allowed matter to prevail, and we still do not know what physical process caused this cosmic favoritism. Uniting the two great pillars of modern physics, general relativity and quantum mechanics, remains the Holy Grail. General relativity masterfully describes the cosmos on the largest scales, the dance of planets and the bending of spacetime. Quantum mechanics rules the subatomic world, a realm of probability and uncertainty. Yet these two theories are fundamentally incompatible. We lack a theory of quantum gravity to describe the primal singularity, the insides of black holes, or the very fabric of spacetime at the smallest possible level. String theory and loop quantum gravity are bold attempts, but a definitive answer still eludes us. These are not mere technical details, they are fundamental gaps in our understanding of existence. The quest to solve them is far from over, driving the next generation of telescopes, particle colliders, and space probes. Our cosmic story is still being written, with its most thrilling chapters yet to come. Our journey through 30 cosmic questions reveals a universe both breathtaking and humbling. We have traced the story from a single point of infinite potential to the vast web of galaxies we see today. From the first fusion reactions in ancient stars to the dark energy now tearing the cosmos apart. We have found answers written in the oldest light and felt in the ripples of spacetime, yet the greatest mysteries still lie just beyond our reach. The true nature of the dark universe, the reason for our existence over antimatter, and the physics of the very first moment remain profound puzzles. This is not the end of our exploration, but a new beginning. Every unanswered question is an invitation, a call to the next generation of thinkers and dreamers to look deeper into the void. The universe is not a solved equation, it is an ongoing story, and we are all part of its unfolding narrative. What single cosmic mystery has always captivated your imagination? Share your thoughts in the comments and join us as we continue to explore the deepest secrets of space.